Hello, chemistry. Today I want to talk to you just a little bit about the different physical states that ionic compounds can have. Normally when we talk about physical state, we're talking about solid, liquid, and gas. So, for water, water can be ice, it's a solid, it can melt into what we typically think of as water, liquid, or we can boil it and turn it into gas. Now for ionic compounds, there are really different two states that they exist in. One is solid, and the other is aqueous. And I'm going to use the compound NaCl to explain this. So NaCl is a very simple compound. It's actually what table salt is made off of. And we know that the ions formed in NaCl are going to be Na positive and Cl negative. So when you see table salt, it looks like little grains of sand or little crushed crystals. And those are sodium and chlorine ions that have basically been locked together, kind of like a jungle gym structure. So this is actually an example of what table salt might look like. So these green circles represent sodium ions. And the blue circles represent chlorine ions. Now, because positive and negative attract, these ions sort of get locked together into what we call a crystal. Sometimes it's also called a crystal lattice, right? And if you think of salt, you can crush it, you can break it, you can hammer it, and it's not going to, if you hammer it, it's not going to change its shape, it's going to crumble, right? That's because of the crystal structure. The crystal structure isn't going to bend, it's just going to break into pieces. So solid, when we're talking about solid salt, we usually write it as NaCl, and that's true for any ionic compound. When we're talking about any ionic compound in its solid form, we usually write the formula. So another example, I could write CaCO3, right? That would be calcium and carbonate in its solid form. Now the other form that ions can exist in, and this is probably the most common, is the aqueous form. And aqueous means dissolved in water. Now you might remember from our unit on food chemistry when I talked about making cheese and I talked about congealing the casein molecules or causing them to coagulate, I talked about water. So here's our water molecule. And one of the things I told you is that water is a polar molecule. That means that it doesn't have any charges, but there's one part of the molecule that's slightly more positive and one part of the molecule that's slightly more negative. So the hydrogen part of water has a slight positive charge. So this little symbol I drew means partial positive. And that just means it's a little bit more positive. And the oxygen is a little bit more negative. And it's not ionic. You haven't had electrons donated from one atom to the other. All this means is that within the covalent bond, the electrons are actually going to hang out a little bit closer to the oxygen than to the hydrogen. Now again, I've told you opposite charges attract. So water is going to really like ionic compounds because ions are charged. So ions really like hanging out in water because the anions, the negative ions, can go hang out near the slightly positive hydrogen, and the cations can go hang out near the slightly negative oxygen. And that's why if you put salt in water, you see the salt disappear. It dissolves. We call that dissolution. And here I've got a diagram of that, of salt dissolving in water. So here's my salt crystal. I put it in water, and all of the little crystal pieces break apart because sodium is now in its ionic form, and it's really happy to be a positive charge surrounded by the negative portion of the water molecule. Chlorine has a negative charge, and it's going to be really happy to be surrounded by the positive charges of the water molecule. So, quick recap. Ionic compounds, this time I'll use a different one. I'll use KBr as an example, potassium bromide, can exist as solids. When they exist as solids, they look like these crystal structures. But as soon as you put those crystals in water, they dissolve. And the reason that they dissolve is that water is a polar molecule, which means it's got these positive ends and these negative ends. And ions love to hang out in water. Okay? So when we talk about aqueous ions, we're talking about the ions that are no longer part of a crystal, but are dissolved in water. And that's when we usually write them, I'll use potassium again, in this form that you've been getting used to. So when I have ions that are aqueous and they've been dissolved in water, I usually draw the ions like this.